So they want me to keep explaining why the flaws in their dopey experiment. So this is an image I created in the last video, and I didn't even notice things about it. So this bar said that this gigantic difference in the parallax, or whatever you want to call it, the way the ruler is seeing the world, and it is gigantic. So if we just go by this little rod here that's holding the rubber band, I mean, it's 16.5, almost 16.4 here, and it's 15.8 over here. So that's a difference of at least 6 millimeters, and he's calling that 2 millimeters. So it's this whole thing.
This is to demonstrate whether or not there is a parallax problem. I'm going to drop the one mass each time from the forehead position. And first I'm going to place the camera over here. Then we're going to see wherever the rubber band comes. We're going to see a number, let's say it comes over here. So that's going to be at an angle. We're going to read the number from the perspective of the camera. Then I'm going to move the camera to the left. I'm going to drop it once again and see whether or not we will read the same number on the ruler. And if those are the same, if the number that you read over here is the same as the number as you read over here, then there is no parallax problem, right? So here we go. Let's first start here. Forehead. Okay, there we go. Now moving it to the left. Do it again. Okay. Maybe a little bit further now. Third trial. Okay, that's it. Here, the maximum stretch was in the center of the camera lens, and it's aligned with 33.2. Then I moved the camera more to the left, so now the maximum stretch is taking place more to the right of the camera. So we're viewing it from an angle. And what we see, it's only 1 millimeter in difference. It's aligned with 33.3. And then I moved the camera even more to the left, so now the event is taking place almost to the outer right in the corner of the camera lens. And what do we see? It still is around 33.3. So there is barely any parallax problem. So whether I move the camera to the left or to the right, the numbers will be seen exactly the same way. It will always be the same number. There is no parallax problem.
So there's so many things wrong, okay, with the whole theory of this. So first he has these rubber bands bound together somehow in this newer experiment. And so who knows what that does? Who knows what rubber bands are any good? They don't make scales out of rubber bands, frankly. Okay, I mean, that would be nice and cheap, right? If you could make a scale out of rubber bands. And so obviously rubber bands get hotter the faster you expand them. They do a lot of things. So maybe they're not even good scales. That they'll always give latitude to velocity. That is, things going faster will be easier to affect the rubber band because the rubber band degrades in its function because of that heat. Now, the key factor, the thing I hadn't noticed until I went through a few of these clips, and I said, wait a minute, is this turning thing. Oh, what the hell was that image? Well, we won't worry about that now. So if you look at this one, goes in nice and straight. So the mass without the one mass is this hollow one. The two mass is this one. Every single case, the two mass is turning to the left. Well, it's turning to the right from its directional. But anyway, it's turning, it's twisting.
No, you are wrong. It's not the same for every single trial. These are the 4 trials for the 2 mass, 1 velocity. This is the one that you showed to your followers. This is the one that twisted the most. However, this example is straight. And what is the difference? Only 1 millimeter, 1 bloody millimeter. This one is going just a little bit twisted. This one is also a little bit twisted. This one is straight. Of course, this is the only one that you show to your audience. So whether it's like this or like this or like this or like this, it doesn't matter. We have the same results, only 1 millimeter in difference at best. So as well for my new experiment, I have many examples where you can see that the pendulum also twists to the left, to the right, or it goes straight, and it doesn't make a goddamn difference. It's always the same result. Okay, so in my new experiment, I'm going to do a whole bunch of trials. I'm going to drop a 1 mass from 1 height, 1 mass 2 height, 1 mass 3 height, 1 mass 4 height, 1 mass 8 height, 1 mass 9 height. Then I'm going to drop 2 mass from 1 height, 2 mass 2 height, 2 mass 3 height, 2 mass 4 height. Then I'm going to drop a 3 mass from 1 height, 3 mass from 2 height, 3 mass from 3 height, and then a 4 mass from 1 height and a 4 mass from 2 height. So I have a whole bunch of different trials that we can compare with each other. And we're going to compare two models, the two opposing models, E equals mgt versus E equals mgh, and then see which one are all in line with which model. Let's find out. So for the camera, first I'm going to center the camera lens with the rubber band so that you can see with which mark the pendulum or the rubber band is aligned with. Okay. Again, the pendulum and the rubber band is really close to the ruler, so when we know this number, we notice this is a fixed location. And then I'm going to move the camera to the left because the rubber band will stretch all the way up here. Okay, if the camera stays over here at this position and the rubber band is over here, then your view you will view it from a really far angle. This is where you're viewing it from, and the rubber band will be over here, and that's a great angle. So when I move it to the left, I can hopefully try to make sure that the rubber band is also centered with the camera lens. Now again, we know that this starting line, the 0 line, is at a certain position. For me, it's around 42 centimeters. So when the maximum stretch is at, I don't know, for 32 centimeters, then we know that the displacement is 10 centimeters. Right, so once again, I have a new cardboard with all the heights, the lines. This is the 0 line. Okay, I'm going to show you that the pendulum, right, this center focus, the center is aligned with the 0 line. I mean the center of mass. You see that, right? And so the 1 height is going to be 4 centimeters. It's going to be right over here. So each time when I'm going to drop the pendulum, I will show you that I am dropping it from within the center of mass, that the center of mass is aligned with the line. Then we have the 2 height, and then we have the 3 height, and we have the 4 height, and then we have an 8 height, and then a 9 height, like that. There we go. This is the 1 mass, 43.75 grams. The 2 mass should be around 87.5. That's 87, okay. The 3 mass should be around 131. So I'm going to add on these two for the 3 mass. It's 130.30, very close to 131. The 4 mass should be 175. I'm going to add these two then, and a little extra. And that is 176, 1 gram more. There we go. These are the masses. Okay, 1 mass, 1 height, trial 1. One mass, 1 height, trial 2. Mass 1 height, trial 3. One mass, one height trial 4. One mass, two height trial 1. One mass, two height trial 2. One mass, two height trial 3. One mass, three height trial 1. One mass, three heights trial 2. Mass, three heights trial 3. One mass, four height trial 1. One mass, four height trial 2. One mass, eight height trial 1. One mass, eight height trial 2. One mass, eight height trial 3. One mass, eight height trial 4. One mass, nine height trial 1. Mass, nine height trial 2. One mass, nine height trial 3. Two mass, one height trial 1. 2 mass, 1 height trial 2. Mass 2 height trial 2. Two mass 2 height trial 3. 2 mass 2 height trial 4. 2 mass 3 height trial 1. 2 mass 3 height trial 2. 2 mass 3 height trial 3. 2 mass 4 height trial 1. Done. 2 mass 4 height trial 2. 2 mass 4 height trial 3. 3 mass 1 height trial 1. 3 mass 1 height trial 2. 3 mass 1 height trial 3. 3 mass 2 height trial 1. 3 mass 2 height trial 2. 3 mass 2 height trial 3. 3 mass, 3 height, trial 1. Three mass, 3 height, trial 2. Three mass, 3 height, trial 3, I believe. Four mass, 1 height, trial 1. Four mass, 1 height, trial 2. Four mass, 1 height, trial 3. Four mass, 2 height, trial 1. Four mass, 2 height, trial 2. Four mass, 2 height, trial 3. Okay, let's first start to compare the results with the model E equals mgt. According to this model, energy depends on how long something falls into gravity, that when you drop an object, it will collect the energy per unit of time rather than per unit of distance. So let's say that you drop an object from 1 height and it takes 1 second. This means that when you drop it from 4 times the height, it will go 2 seconds or twice as fast. When you drop it from 9 times the height, it will take 3 seconds or 3 times, it will go 3 times as fast. This means that when you drop it from 2 height, it will go 1.41 times as fast. When you drop it from 3 times the height, it will go 1.73 times as fast. When you drop it from 8 times the height, it will go 2.83 times as fast. So, okay, this being said, this also means that according to this model, a 1 mass dropped from 4 times the height and a 2 mass dropped from 1 height should be the same. They have the same momentum, so it should be the same energy. However, according to kinetic energy, you have to multiply it times the height. So 1 mass times 4 height is 4. 2 times 1 is 2. This one has twice the amount of energy than this one, according to kinetic energy. So that should result into around 1.4 times the amount of stretch in the rubber band. So let's take a look. 1 mass 4 height, which is 8.85, and a 2 mass 1 height, 6.63. So 8.85 divided by 6.63, which is 1.33, which is closer to the 1.4 number than to 1. Next, the 2 mass 4 height should be the same as 4 mass 1 height. They have the same momentum. However, according to kinetic energy, 2 times 4 is 8, and 4 times 1 is 4. So this one has twice the amount of energy than this one. So that should result into 1.41 times the stretch. 2 mass 4 height is 12.13. 4 mass 1 height is between 8.85 9.1, so let's take 9. All right, so 2 mass 4 height, 12.13 divided by 4 mass 1 height and 9, which is 1.34. Again, closer to the 1.4 number. Then, hold on. Yeah, so the 3 mass 1 height and the 1 mass 9 height, that has the same momentum. However, according to kinetic energy, 3 times 1 is 3 and 1 times 9 is 9. So this one has 3 times the energy than this one. Now that would result into the square root of 3. So the rubber band should stretch around 1.73 times as much. Let's check it out. 1 mass 9 height is 12.65. And then 3 mass 1 height, 8.15. That gives us 1.55. So it's a little bit below the 1.73 or 0.2-ish. So now this column, 1 mass 2 height, 2 mass 2 height. This one has twice the amount of momentum than this one. According to kinetic energy, also this one has twice the amount of energy as this one. However, I assume that this model predicts that it will produce twice the amount of stretch in the rubber band. However, kinetic energy says no, it should be around 1.41 times the amount of stretch. Whenever something is twice the energy, according to kinetic energy, it should produce 1.41 times the amount of stretch, not twice the amount of stretch. Twice the amount of stretch should be 4 times the energy. So let's check it out. 2 mass 2 height, 9.075, 9.075 divided by 1 mass 2 height, which is 6.4. Look at that. It's a perfect 1.41 number. So the same with this one. 1 mass 3 height, 2 mass 3 height. This one has twice the amount of momentum, and the kinetic energy also, this one has twice the amount of energy. 2 mass 3 height, 10.72 divided by 1 mass 3 height, 7.77, and that's 1.38 almost. So very close to the 1.4 number once again. Then 1 mass 8 height, 4 mass 2 height. Once again, this one has twice the amount of momentum. Kinetic energy also says it has twice the amount of energy. So 4 mass 2 height, let's check it out. 12.45 divided by 1 mass 8 height, which is, oh, I was wrong. I'm sorry. It's the same, 12, 12. Oh yeah, of course. Because 1 times 8 is 8, and 4 times 2 is 8. Yeah. Yeah, so this one has twice the amount of momentum than this one. However, according to kinetic energy, it has the same energy. 1 mass times 8 and 4 mass times 2, that's the same. And so we have the same, 12.45 and 12-ish. So it's the same. Kinetic energy wins. All right, next. 1 mass 4 height, 2 mass 4 height. So again, this one has twice the momentum, and 1 times 4 is 4, 2 times 4 is 8, so also twice the amount of kinetic energy. So let's see, 2 mass 4 height, what was that? 12.13. 12.13 divided by 1 mass 4 height, which is 8.85. 8.85. 1.37, once again, kinetic energy wins. Then 1 mass 4 height, 4 mass 1 height, 4, yeah, so it's the same according to kinetic energy. 1 mass 4 height and 4 mass 1 height, it's the same. According to momentum, this one has twice the amount of, according to MGT, this one has twice the amount of momentum, so twice the amount of energy. Let's take a look. 1 mass 4 height, 8.85, 4 mass 1 height, yeah, 8.85 between 8.85 and 9.1. So yeah, once again, kinetic energy wins, obviously. And there you go. Those are a whole bunch of significant cases in a row, each time showing obviously that the results and the predictions are a lot closer to what kinetic energy, or E equals mgh, predicts. Okay, and now comparing the results with the E equals mgh model. So according to E equals mgh, 1 mass 2 height is the same as 2 mass 1 height, because 1 times 2 is the same as 2 times 1. So let's take a look. 1 2 height is 6.4, and the 2 mass 1 height is 6.6. So pretty close. Then the 1 mass 3 height is the same as the 3 mass 1 height. Let's take a look. 1 mass 3 height is 7.77, and 3 mass 1 height is 8.15. Difference of around 3 or 4 millimeters. Then the 1 mass 4 height should be the same as the 4 mass 1 height, should be the same as the 2 mass 2 height. 1 mass 4 height is 8.85, and then the 4 mass 1 height between 8.85 and 9.1, that's close, and then 2 mass 2 height 9.075. It's all pretty close. Then the 3 mass 2 height should be the same as the 2 mass 3 height. 3 mass 2 height 10.7, then 2 mass 3 height 10.72. That's almost perfect. That's perfect. Right, 1 mass 9 height, that should be the same as 3 mass 3 height. 1 mass 9 height is 12.65. 3 mass 3 height is 12.52. Really close. Then 1 mass 8 height, the same as 2 mass 4 height, the same as 4 mass 2 height. Right, 1 mass 8 height is 12.075. 2 mass 4 height, 12.13. And the 4 mass 2 height, 12.45. They all are almost exactly the same. Now, I just wanted to also show you that when something has 4 times the energy, that should result into twice the amount of stretch, of rubber band stretch. So 1 mass 1 height, 1 mass 4 height. Let's see. 1 mass 1 height, 4.75. 1 mass 4 height, that's 1 mass 1 height, yeah, 4.75. 1 mass 4 height, 8.85. That is, yeah, it should be around 9, I guess, times the amount of, well, let's put the calculator, right? 8.85, hold on, 8.85 divided by 4.75, which is 8.6, 1.86. So it's a bit below the 2. 2 mass 1 height, 2 mass 4 height, that's 4 times the amount of energy. 2 mass 4 height, 12.13. And then 2 mass 1 height, 6.63. Also 8.83-ish. Should be 2 to ideally. Then 1 mass 8 height, 1 mass 2 height. Right, 1 mass 8 height, 12.075 divided by 1 mass 2 height, which is 6.4, and that, hold on, I'm sorry, 12.075 divided by 6.4, right? 1.88, so it's all pretty much the same-ish, all around 1.8, 1.9. Then 1 mass 2 height, 4 mass 2 height, and let's see, 4 mass 2 height, 12.45 divided by 1 mass 2 height is 6.4. That is 1.49. That's pretty close. All right, so that's it. I think, well, it's certainty. This absolutely proves the case that E equals mgh is the reality. This is way too significant. So many examples. All the results are way more in line with this model than this model. Come on. Of course, you're going to come up with more excuses. You're going to say it's flawed, it's garbage, it's crap, etc., blah, blah, blah. But how the hell, why do all these flawed experiments always coincidentally are matching the predictions of this model? How the hell is that possible? It's always very significant that they are so close to the predictions of what kinetic energy predicts. I don't understand.